All right, welcome class to lecture 23. This is our last lecture in the module that we've been considering, in which we have developed a theory for reaction rates by considering the statistics of rare events. Specifically, we have been largely concerned with unimolecular processes, some abstract A going to some species B. We can have in our mind some simple reactant transversing to a product by maybe isomerizing or reacting, losing some leaving group. We could imagine a polymer folding or a collection of particles assembling. In each of those cases, we've identified a means of computing the rate of A going to B by the dynamical fluctuations which move particles between those states, or the system more generally between those states, introducing the so-called side-side correlation function. Or its equivalent, the so-called flux side correlation function. So those are, as long as the rate exists, exact expressions that will give you the time scale over which one has to wait on average to see A going to B. We've made a couple approximations and developed a few theories around those approximations to make these calculations tractable and intuitive. The first that we introduced was so-called transition state theory, which neglects the fluctuations, the dynamics for which the system traverses the barrier and takes a zero time limit. It approximates the rate as just this initial value of this correlation function in the flux side correlation function. Which means that the flux has to go in the direction that would enable a reaction to occur. So it needs to be pointed in the positive direction of some reaction coordinate Q. And the rate then is just given by the flux over that barrier times the ratio of probabilities to start in basin A and get up to that transition state. So the picture we have in the back of our minds is motion on some free energy or potential energy surface, whereby local relaxation can occur in one of the wells, say the A well, and over much longer times, there will be a rare fluctuation that traverses a barrier, bringing it into the B, and we imagine that we can pick out Q, the reaction coordinate, and identify, in order to apply transition state theory, the relevant dividing surface, the bottleneck through which dynamical fluctuations have to develop in order to see that reaction occur. Provided that identification of the relevant reaction coordinate, one can compute transition state theory from purely thermodynamic expectations. This ratio here is going to be given by a ratio of, or a difference in free energies. The flux is just a thermal flux that's going to be proportional to kBT, maybe the mass of that mode, etc. And we spent then along, a lecture discussing how to relax transition state theory, invoking things like Kramer's theory, in Grota and Hines theory, which are theories that model the dynamics at the top of the barrier in different ways as a means of computing kappa, the so-called transmission coefficient, which with the transition state theory estimate will give you an exact estimate of the rate. And with different approximations, like the barrier crossing being overdamped or underdamped, Markovian or non-Markovian, one can get different forms for kappa. We then applied this construction to Marcus's theory of electron transfer. Which began a discussion concerning how exactly we should choose this reaction coordinate. That's something that we have largely neglected having a more holistic discussion on. We talked about how Marcus had unique insight into picking a solvent coordinate to be associated with the reaction coordinate. In a specific case, Q was given by some energy gap associated with moving the electron from the donor to the acceptor. And with that insight, he was able to apply transition state theory without much problem, without needing to correct for dynamics at the top of the barrier. If you, in general, find the relevant saddle point, the relevant dynamical bottleneck, transition state theory will give you a good estimate. In fact, we know that the transmission coefficient is bounded from above by 1 and saturates at 1 when one can really neglect recrossing events, when one can neglect dynamics at the top of the barrier. So in the limit that you've picked the barrier height, the position of the barrier, which really is maximally unstable, you'll have a good estimate of that rate. So what I want to talk about today is how do you determine more generally what the reaction coordinate is? If I gave you an arbitrary dynamical process, a rare event, some reaction A goes to B, and ask you onto what degree of freedom, what reaction coordinate should you project that dynamics in order to understand it mechanistically and apply things like transition state theory to estimate the rate of that rare event, what would you do? So the short answer is that it's hard. It will always be hard. It's a very difficult thing to know what the dynamically relevant reaction coordinate is. There are lots of rules of thumb. One can work from concrete models where the reaction coordinate is understood, like Marcus's theory. So you have maybe some intuition from that theory that anytime charge is being moved around, that especially in a polar environment where fluctuations of the surrounding solvent can modulate energy scales by enormous amounts, that maybe the solvent would be an important player in the reaction coordinate. You also know in cases like simple gas phase reactions where there's very few degrees of freedom, that maybe just the bond length is a good reaction coordinate because that's something that has to be extended in order to break a bond. So there are limiting cases where Q might be simple, but imagine, if you will, you were trying to apply transition state theory to protein folding. What then is the right reaction coordinate? How would you think about motion on a low-dimensional surface that gave you insight into the reaction and lets you estimate the timescales with which it happens? To understand how this can be difficult, especially in high-dimensional systems, let's imagine taking our usual plot, some free energy as a function of Q, to exhibits metastability with a single barrier in between, and construct a free energy in 2 dimensions that could reduce down to omega of Q. So, for example, let's imagine that there exists some Q prime that when I integrate out Q prime from some joint free energy F of Q and Q prime, I get back omega of Q. This is a non-unique mapping going backwards. There's many different functional forms of this joint free energy. That could give rise to the specific omega of Q that we see below. A particularly pathological example one could imagine would be something like this. I call it particularly pathological because in our low dimension projection, if we were to observe dynamics on just Q, we might see that, for example, a reactive trajectory just monotonically increases in Q. That would be incredibly deceptive if we viewed it in a fuller dimensional space where, for example, if this was the free energy the system was actually evolving on, there's clearly motion needed in both Q and Q prime in order to react. Going straight in Q would be incredibly unfavorable. I'd have to go much higher in free energy than I actually need to in the full dimensional space. Therefore, in general, high dimensional systems, projections onto low dimensional coordinates can be misleading, can miss important dynamical effects, even though by construction, the free energetics are exactly conserved. If I wanted to know how probable it is to be in A or B, I don't need to know about Q prime. Thermodynamics tells me that I can integrate out whatever I want. And as long as Q acts to separate those two basins, I will be able to preserve the equilibrium ratio of partition functions, the equilibrium constants between A and B, but not their dynamics. The dynamics depend through the equation of motion on all coordinates in principle. To understand this a little bit more, consider our reactive flux calculation, the flux side correlation function. If I started at the top of the barrier and only knew about Q, I might imagine that with equal probability, I could go left or right. That at A configuration, if I happen to do a Maxwell-Boltzmann distributed velocity that points me in the right, I would end up going to B. If I happen to draw a Maxwell-Boltzmann distributed velocity that's pointing me to the left, I would go to A. However, from this two-dimensional picture, it should be clear that if I happen to pick a configuration at Q star that was here, it doesn't really matter what velocity I get, as long as it's not really big negative. Overwhelmingly, I'm going to go to the right. Analogously, if I drew a value of Q star that points me there, I'm overwhelmingly going to go to the left. You can kind of see how recrossings can occur due to higher dimensionality. So then, how should you discover variables like Q prime? What would you need to do if you had a high dimensional system in your hands whose reaction coordinate you wanted to understand? Should you go about uncovering the meaningful dynamical variables. So today we're going to talk about 3 things in total. The first 2 deal with this question directly. We will discuss some formalism that introduces quantities that help you uncover this behavior, so-called splitting probabilities and committer functions, that if you had in your hand a specific model and the ability to propagate dynamics, one could compute and use those functions to uncover meaningfully dynamical coordinates. Of course, rare events are made difficult by the fact that they are rare, that it can be difficult to observe many examples of reactive trajectories if you are just propagating dynamics straightforwardly. And so we'll introduce a tool that has been used to efficiently harvest reactive trajectories without underlying the mechanistic assumptions. This is known as transition path sampling, a means of sampling an ensemble of trajectories that is by construction reactive. And then finally, we'll conclude our discussion of reactions and rare events with a slight generalization of what we've been doing thus far into bimolecular processes, in which rare fluctuations both in space, through space, physical space, how 2 reactants meet each other to react, are coupled to rare fluctuations along the reaction coordinate that allow them, once they have found each other, to react. So in general, bimolecular processes can operate in limits where either diffusion is rate limiting or the actual reactive event is rate limiting. We'll work out a little theory using the Bimolecular equation to sort that out. Okay, so let's consider and introduce the notion of a splitting probability. And committer functions. So let's introduce a function phi subscript b for a given coordinate configuration of the system. So I take the full dimensional space, all the positions of all the particles, that goes into the argument of this function phi b. This is the committer. It is equal to an average over a velocity distribution. Most case, this is an equilibrium velocity distribution, so this is a Maxwell-Boltzmann distribution of velocities. And what it averages is our side step function, which will depend on the specific realization of the velocities, the specific configuration I'm starting on, and will be propagated some short time, tau mole. So this function, HB, binary variable, gives us 1, as we've defined previously, if in basin B, 0 else, it's binary variable, it's being averaged over a distribution of velocities. And so it is the probability that a specific configuration, R to the n, reacts. after some short amount of time, tau mole. So I pick a configuration, I run the dynamics from a Maxwell-Boltzmann distribution of velocities for a short amount of time, and I ask, do you react? Is this a reactive configuration? Is it sucked into the basin of attraction of B? We could pictorially illustrate this. Imagine that this is basin of attraction A, what we mean by our reactant state. Here is B. Maybe there is an example of a reactive trajectory with configurations along the way. I could pick this configuration, integrate trajectories from a Maxwell-Boltzmann distribution of velocities, and likely see that overwhelmingly those are committed to basin A. So in this case, phi of B would be 0 for that specific configuration. Analogously, if I were to pick a configuration near the basin of attraction B and integrate trajectories, maybe overwhelmingly, they will be sucked into B, in which case this committer function, this probability of reacting would be very high, maybe even 1. For a reactive trajectory, there exists at least one configuration. Let's imagine it's this one, where if I play the same game, some trajectories will not react, or some realizations, rather, of the velocity distribution will cause the reaction to occur. Others will not. And on average, this is a configuration which is maximally uncommitted. It could either end up in B or A. Those configurations for which phi of B equals 1/2. There are many reactive trajectories, many realizations of a reaction. They will thus have many, they will thus generate many configurations for which this committer is equal to 1/2 criteria is valid. And thus one could say that there is an ensemble of configurations for which phi B is 1/2. And we would call that ensemble the transition state ensemble. The transition state, when we think back to this picture, we are imagining implicitly that those are the configurations which are maximally undecided, that could go right or could go left. That's the assumption in defining dynamical significance to that transition state, to that saddle point. I could be easily tipped to react or easily tipped to not react. In a high-dimensional system, where locating one single saddle point might be difficult, locating a saddle point generically might be difficult, and moreover, there might be many, many saddle points on some very high-dimensional surface, there is more utility in using the dynamics to decide for you what are those configurations which satisfy the same idea we have of a transition state, that it's maximally uncommitted. So this gives you a process for which you could uncover a collection of configurations which are all near some dynamically relevant saddle point, which you then could use to look at, interrogate, and ask, what do those configurations have in common? How do I categorize them in such a way that they all have the same value of some reaction coordinate? We can get some formal insight into what this committer function looks like by computing one exactly for a low-dimensional system, say evolving with overdamped dynamics. Gamma x dot, let's do q. Q dot is minus the gradient of this free energy plus some noise. As usual, gamma is the friction, eta is a Gaussian random variable. We know that that equation generates a Shmolekowski equation for the evolution of the probability density of Q at some time t, which could be written as the gradient of a flux, where that flux depends on the diffusion constant and that potential. If we solve this equation with boundary conditions, rho of Q at 0 is a delta function. At some Q naught, and rho of Q A at time t is 0, while rho of Q B at t is 0. So we have some initial source and set of sinks in the two basins. We can compute the committer as an integral over all time of the flux into B. So we start at Q naught. We dictate that there is no probability at long times in any of the basins. And if we add up the flux that went into B, rather than going into A, which there's also a sink, so probability will leave there too, then we can say with what probability, with what splitting probability, if I start at Q naught, do I end up in B? You can manipulate that flux, and what you'll find is that it is given by an integral over Q from QA to Q naught, where this QA is usually taken as the bottom of the well in basin A, an integral over the Boltzmann factor flipped upside down, divided by the same, but rather integrated from QA to QB. That's all of the support associated with the distribution where there's sinks at A and B. This is something that will go as a probability should between 0 and 1 and will be sinusoidal. So if, for example, we have our usual one-dimensional reaction, where we do have one transition state. This committer function will be 0 if I start over in state A. It'll go to 1 as I get in state B. And it'll cross over at a half exactly at Q star. Where in this one-dimensional example, we know exactly what Q star is. And it has a width that depends on the height of the barrier plus or minus kBt. So indeed, that we expect that phi b, as you'll prove in your homework, is a monotonically increasing function with a unique point where that line passes through 1/2. And so if you can harvest a lot of trajectories, compute those committer functions, you can generate an ensemble of transition states that you can interrogate, and thus find their commonalities, thereby uncover mechanism. In addition to then potentially computing a free energy along that coordinate to use as a transition state theory estimate of the rate. That's all well and good. However, you should be thinking, if the rate is rare, if the rate is small and the event is rare, then how am I supposed to generate a whole bunch of reaction examples to then interrogate? So to understand that, and the transition path sampling algorithm that solves that problem, let us first introduce a notion of the reactive path ensemble. So as before, we can think of a fundamental object for which to assign a probability to being a trajectory, a sequence of points, chronologically ordered from some initial condition x0 to some final condition x of t. We can, as we have, assign a probability to observing that path, call it P0, which is the probability of seeing the initial configuration. We can, for simplicity, imagine that this is an equilibrium distribution. And, and then Q, or P0, is the conditional probability of generating that trajectory from that initial condition. And for example, if we're evolving with stochastic dynamics, this would be that conditional probability would be some Onsager-Mach form. If we're evolving with deterministic dynamics, that's a set of delta functions. This P0 here is any arbitrary trajectory. We can filter out only those trajectories which do something interesting, like go between A and B, by conditioning it, taking our initial path probability and setting the weight to 0 for all of them that don't start in A and don't end in B. Now, if we do that, P0 is no longer normalized. So there is some new normalization constant, call it ZAB. So this is the probability of finding a reactive trajectory. That goes from A to B. This ZAB is a partition function. It's renormalized a probability distribution that counts how many reactive trajectories there are. By construction, it is going to be given by an integral over all possible paths, the probability P naught of observing the path unconditioned, and those weighing factors that say that I start in A and I end in B. Notice that this partition function can be thought of as an expectation value. It's an integral over a probability that starts normalized. And so one can consider that path partition function as an expectation value, HA at 0, HB at T, averaged, of course, within the dynamics described by P naught. Analogously, we could define a partition function ZA, which is an integral over paths. The weight or probability of finding that path conditioned on starting in A at time 0. By construction, that's just an average of the operator HA. So while ZAB counts the number of reactive trajectories, ZA counts the number of trajectories that start in A. Looking at those two expectation values should ring some bells. If I took their ratio, HA at 0, HB at T averaged over HA at 0, that is defined as this ratio of partition functions, ZAB over ZA. ZAB has a formal dependence on time because it is a 2-time average, ZA does not. We know what that ratio is. That's CAB, the side-side correlation function. Its derivative gives us the rate, and in steady state, that ratio must go like KAB times T. So what we've just found is a relationship between a rate constant and a ratio of path partition functions. Thus giving a physical interpretation as to what a path partition function is. If you will remember, a ratio of configurational partition functions is related to a free energy. If I gave you the configurational partition function conditioned on being in one state or a set of other states, that would be related to, through a logarithm and a minus kBt, a change in free energy from going from one state to that collection of other states. Here, if I condition on trajectories that do something like react relative to those that don't, that are just conditioned to start in a given state, that ratio of path partition functions is exactly proportional to a rate constant. This should make intuitive sense given how we formulated ZAB and ZA as just the number of trajectories that react relative to the number of trajectories that just start in A. Perhaps more provocative, is to consider the analog of a reversible work, but in path space. In equilibrium, because, as I've just reminded you, ratios of partition functions are related to changes in free energy. Free energies are the reversible works associated with some transformation. Here, a ratio of path partition functions can be thought of as a reversible work, but in a path space, in a space of trajectories. Okay, so what does this reversible work mean? It's the work to transform a trajectory that starts in A into a trajectory that goes from A to B. So if we drew some example trajectories, so a trajectory that just starts in A, overwhelmingly, if I just picked one out of the hat, would just go back to A. So I could imagine that my initial conditioning is very broad, it doesn't depend on anything. But I could imagine taking that trajectory, imagining it's like a little polymer, and making sure that it at its endpoint began approaching basin B, maybe pulling it that much in one step or all the way to B in subsequent steps. Where these blue lines are meant to be constraints on the endpoint of the trajectory. So this would be a reversible, this could be a reversible work path that grows a trajectory from being localized in A to begin with to one that traverses a barrier in some high dimensional space and goes eventually between A and B. This means that in principle, there is a reversible work path. So if it's a reversible path, it's independent of how exactly you create that transformation, independent of the specific mechanical path I might take a thermodynamic system through to compute a free energy. If I do each step reversibly, the free energy is just a state function. It just depends on the endpoints. Analogously, this is suggestive of the notion that one can construct reversible works in path space, and thus independent of those details of how you decide to draw these constraints, compute the rate. In this case, the rate is just a product of these endpoints also. It's a state function in the path space. In principle, how would you do this? Just like you sample rare values of magnetization in the Ising model when we do Monte Carlo in configuration space, one could construct a Monte Carlo algorithm in path space and impose constraints, for example, where the endpoint of the trajectory is. That's what transition path sampling does. And with transition path sampling, one can importance sample the endpoint of the trajectory to compute the reversible work to grow a reactive trajectory and thus compute the rate. Transition path sampling, of course, being something invented here at Berkeley by David Chandler and his then student at the time, Phil Geisler, who you all probably knew. All right. So that's transition path sampling. If you want to learn more, you can ask about it in the small group discussions. I'd be happy to sketch out what the metropolis acceptance criteria look like for different sorts of moves. What's nice is that largely those acceptance criteria are pretty straightforward. So let's wrap up today. Spend the last 20 to 30 minutes or so discussing different sorts of reactions, those that require two molecules to come together for the reaction to proceed, so-called bimolecular reactions. So rather than A going to B, we're envisioning that A plus B goes to some C. We will consider this sort of process happening in solution so that these two molecules, A and B, first have to diffuse around the solution, find each other, and then react to get to C. So macroscopically, such a process, as long as A or B is not expressed in overwhelmingly high concentration, will follow second order kinetics. I wanted to ask for the rate of change of the concentration of B in time. This would be given by the probability of finding some B, given by its concentration, times the probability of finding A, given by its concentration, and then a number, the rate, that tells me that if I find those two species, I can react. I can lose concentration of B with some rate. Now it's second order, so-called second order kinetics, because it depends on two factors of concentration, A and B. Probabilistically, while in first order kinetics, the rate constant can be interpreted as the probability of a reaction occurring per unit time. Here, the factor K times rho B has the same interpretation. So the product of K and rho B is a probability to react per unit time. Which means that K is the probability to react per unit time per unit concentration of B, or per unit probability of finding B, and rho B, the corresponding probability to find B from the perspective of, for example, A. That per unit time has the same interpretation here. It is some molecular timescale, like tau mole, needed to define the probability to react per that unit. Some molecular timescale that signifies the minimal amount of time it takes to cross the barrier, given you're about to do so. So a lot of the structure we've had previously carries over. But now we have to worry about not just the reactive event itself, given A and B are close enough to each other for that to happen, but now we need to understand how that is mitigated or modulated by the fact that those two species have to diffuse in solution. So let's assume that diffusion is overdamped. So this is really happening in solution, not in the gas phase, where mixing is going to be largely fast. Motion will be ballistic in between collision events. If it is overdamped, then each species I will diffuse around due to intermolecular forces F and random forces eta with potentially their own friction coefficients. A and B need not experience the same amount of friction as they move through the solution. However, for simplicity, let's imagine that that gamma is constant. If they diffuse in an overdamped way, then each will follow a Shmolekowski equation dictating that the probability of finding B at position R and time t, let's make this an R, and how that changes in time in now 3 dimensions is given by the gradient of our flux at R and t. And that flux is given by minus beta times d. Sorry, no beta there. Minus d e to the minus beta, some potential v of r, times the gradient e to the beta v of r times rho b of r and t. Where here d is the diffusion constant of B, and V of R is dependent only on R, so it's assumed to be some spherically symmetric interaction potential between A and B. Some effective intermolecular interaction mediated by potentially the surrounding solvent, could be complicated, longer, short range, but convergent if we do its integral. So we can proceed like we did in Cramer's theory and work with a couple boundary conditions to solve for the reactive flux with which the concentration of B is changed. if we are really moving in a solution has translational invariance, we can break that by picking A to be located at an otherwise arbitrary origin. Let's assume at large R, so very far away from the origin, that rho of B at time t is maintained at a constant concentration rho bar of B. So this is some bulk concentration that's held fixed. So we are running this reaction forward enough to compute a rate, but not so much to significantly deplete the solution of B. The short range boundary condition is a little bit more complicated. So this long range acts as one boundary condition. The short range we will assume that there is a constant flux. We want to solve this problem in steady state. So we'll work with one boundary condition that imposes a constant concentration that continually feeds a reactive flux, and something that is more akin to a von Neumann boundary condition, a constant flux boundary condition that says that the loss of B at some R star for all times is equal to minus that phenomenological rate times rho B star bar. So this will impose a constant reactive flux across a dividing surface in the radial distance from species A pinned at the origin that is constant across R star. And proportional to the concentration of B at that value R star. With those boundary conditions, we can solve the Bimolecular equation, working with the fact that the problem has radial symmetry. So these are point particles, rotationally invariant. They interact through a radially symmetric potential. So no particular value of theta or phi in a spherical harmonic coordinate system would be important. We only need to worry about the radial dependence. So the flux at little r, some distance away from the origin, is going to be given by the diffusion constant times that Boltzmann factor associated with the intermolecular potential and a derivative of that Boltzmann factor upside down times rho B at R. To ensure that we do not build up or deplete concentration at each constant shell a distance r away from the origin, we need to ensure that this is equal to some number divided by 4 pi r squared, where that number is the rate of loss of B times the concentration of B out at the origin. So we have spherical shells for which, when averaged over or integrated over the full shell, the flux is constant. Locally, that flux is J naught. So the denominator there is the area of each radial shell. And the numerator, J naught, is the reactive flux in each shell. Let's define a B of R, which is this inverse Boltzmann weighted concentration of B, such that we can rearrange. Here's our B of R. We could rearrange this equation to say that the spatial derivative of B of R is equal to inserting this equality. The negatives cancel. I have J naught over 4 pi D, an inverse Boltzmann factor, divided by R squared. So we have a first order differential equation that we could integrate. At our boundary condition, so B of infinity less B of capital R star. The J naught, 4 pi, and D are constants. And in addition, we'll have this factor lambda inverse, which is the integral from R star to infinity of this upside down Boltzmann factor over R squared. That has units of length inverse. And thus we denote it lambda inverse. So there's a new characteristic length scale that characterizes the scale over which the interaction potential changes. Assuming that potential is finite, range, and bounded, such that V of R goes to 0 as R goes to infinity. We can rewrite rho bar star as rho bar, the infinite R boundary condition, the bulk density of species B, less J naught over 4 pi d lambda, and a factor of now the Boltzmann weight evaluated at r star. This is using our large R boundary condition. Now we can eliminate J naught because J naught was just K times rho B bar. This gives us that the concentration at this inner boundary R star is given by 1 minus the rate constant K, 4 pi d lambda, the bulk concentration of B, and e to the minus beta V at R star. That's the concentration of B at R star at steady state. Ooh. We have J naught is equal to K times the bulk density, which must also be equal to K star, the rate at contact times the concentration at contact. Fluxes are equivalent everywhere, which means that we can substitute rho B star for K over K star times the bulk concentration of B, or finally that K is equal to 4 pi d lambda 1 plus 4 pi d lambda over K star e to the minus beta V star. So we have a description of the macroscopic bimolecular reaction rate, which depends on the diffusion constant. It also depends on the length scale over which particles interact, lambda, in addition to the intrinsic rate of reaction, the rate of reaction at contact, this K star, times the probability of finding that those species at that particular value of R, which is Boltzmann distributed and thus goes like e to the minus beta V star. So there are two clear limits. That you are likely all familiar with from basic chemistry. There is the diffusion limited rate, where the reaction can't keep up with the slow diffusive flux. This is when d lambda over K star goes to 0, in which case the bimolecular rate is just limited or just given by the diffusion constant times some molecular length scale lambda, which again tells you over which lengths A and B will interact with each other. So again, this is a limit where the rate, the intrinsic rate of reaction, the barrier crossing event, is large relative to the time it takes for molecules to find each other as given by their diffusion constants. The alternative limit is, of course, the reaction limit. That's when d over lambda, or d times lambda over k star is much, much greater than 1, likely owing to the fact that the intrinsic reaction rate k star is very small. In that limit, we have in the denominator something that is getting very, very big. I can neglect the 1, and the factors of 4 pi d lambda will cancel. And I will get that the bimolecular rate now is just given by the intrinsic reaction rate, the barrier crossing event, times the probability to find the set of molecules A and B at point R star. So the two limits are 1, where the bimolecular rate just depends on the diffusion constants, how particles move through the solution. When they move very quickly, then the bimolecular rate depends on just the intrinsic reaction rate, the characteristic time over which the barrier crossing or the activation of the complex occurs. In general, if both are comparable, that bimolecular rate will depend on both reaction and the rare barrier crossing, in addition to the probability of finding those species at exactly that contact displacement for which they are allowed to then react. All right. So that's all I really have for today. So we've just concluded our discussion of rare events and reactions. As said at the top, we started with a basic relationship between microscopic fluctuations as encoded by time correlation functions, and what that meant for evaluating the rate constant given to us or measurable through first order kinetics. We developed some theories for considering the dynamics at the top of the barrier, which correct transition state theory. And we talked a little bit about today what is really meant by a reaction coordinate, how you would go algorithmically finding it, how to think about it in high dimensional systems where the reaction mechanism is maybe not obvious. We found an analogy between our previous discussion of path ensembles and reactive events, namely this identification of a ratio of path partition functions giving you the rate of some rare event, and thus illustrating a relationship between reversible work processes in trajectory space and rate constants, an analogy which can be utilized computationally to calculate rates without mechanistic assumptions, invoking the independence of a reversible work on the path that you take, in path through trajectory space in this case. And finally, we've just concluded with a brief generalization from a unimolecular process to a bimolecular process, where in addition to a rare barrier crossing event, it could be, if molecules move slowly, that what actually limits the turnover, the production of some species C from the reaction of A plus B, that in such cases, diffusion can control that bimolecular rate. And in cases where diffusion is fast, so you are swinging around your stir bar and your beaker, mixing things up, the rate of a bimolecular process will be limited by the intrinsic barrier crossing events and the probability to find those species at the right displacement such that they can react together. We used our Shmolekowski equation, which follows from our Langevin equation, invoking reduced descriptions of dynamics for tagged particles moving in baths that they're weakly coupled to. So invoking our basic ideas of linear dynamic models we developed about a month ago, to a problem, diffusion limit kinetics, which is pretty nonlinear. This really marks the end of our discussion in dynamics. Moving forward, beginning with lecture 24, we will change directions for the last time this semester. And rather than continuing a discussion on nonlinear dynamical phenomena, we'll reconsider static phenomena, which exhibits the mother of all nonlinearities, specifically phase transitions and critical phenomena. So in the next remaining lectures, we will build a theory of phase transitions on a field through a field theory representation, so-called Landau theory, which provides great unifying structure for considering nonlinear responses where collections of molecules conspire to generate really discontinuous behaviors. And that'll take the remaining 4 lectures or so. We'll establish this for places we're comfortable starting, like magnetization, and generalize it to pretty sophisticated transitions like those occurring in block copolymer melts. All right, so that's all I have